So welcome everybody to our first example of binomial series expansions. So the idea behind our binomial series expansion is that we are really kind of extending our familiar binomial theorem. And for that, remember that we just had something that we were expanding an expression x plus y to the n power. That thing would look like our sum of k goes from 0 up to n of our binomial coefficients n choose k for x to the k y to the n minus k power. And so as long as n was going to be some kind of positive integer, then this expression made sense because we had values for our n choose k. We can calculate them according to the formula n factorial over k factorial and n minus k factorial. Well, where we do our extension comes in this formula that we just wrote down. Okay, if we imagine kind of writing down n times n minus 1 times n minus 2 down to n minus k plus 1, n minus k, all the way down to 2 times 1. So if we wrote out our factorial on top, that's what we would have. On the bottom, we would have our k factorial, but then we'd have our n minus k minus 1, all the way down to 2 times 1. So that what happens in this case, we kind of see that our n minus k factorial will cancel with a bunch of n minus k factorials on top. And so what that will leave us with is just an expression of the form n times n minus 1 times n minus 2, all the way down to n minus a k minus 1. And then we have in the denominator just a k factorial. Now, what this expression allows us to do is to kind of count the number of terms that we have on top in terms of the index k that we have. So we know that we're just going to subtract integers down to k minus 1 from 0 up to k minus 1, and that's how we obtain our numerator. What this allows us to do then is to expand our notion of the values we can have for n. So we could really let n now at this point be anything that we really wanted it to be. So kind of using this new expression, so let's switch. Instead of calling it n, let's call it r, because we're going to allow it to take on other values. So if I want r choose k, then I'm calculating that as r minus 1, all the way down to r minus a k minus 1, all over a k factorial. So if I wanted to do something like a 1/2 choose 3, I would know how to do that just from this formula by just saying, well, I'm going to have r be 1/2, so 1/2 minus 0, 1/2 minus 1, and 1/2 minus 2, all over a 3 factorial in the bottom. So what this really gives me is a 1/2 times a negative 1/2 times a negative 3/2 over 3 factorial. So that in calculating this, I have a 3/8 times a 1/6, and that is going to give me a 1 over 16. So I'm really able to extend all of my values now from just being positive integers to now I can let r be anything that I want it to be, and so I can obtain expansions of that. So how does this change my binomial theorem? Well, now I can say that I have a binomial expansion. And that thing will be of the form, I can take my expression 1 plus x to the r power. So now I can let r be anything that I want it to be. But now, because my index doesn't have to stop at a particular place, then I can really let my index go from 0 up to infinity, and I will still have my r choose n, and then my power series expansion, x to the n power. And so anytime that I'm doing a binomial series expansion, this is really what I'm talking about. So r can be kind of any value that I want to put in there at this point. So if we kind of look and see what problems they want us to solve now, let's see what we have. So here we're asked to find the first 4 non-zero terms of the binomial series for the cube root of 1 plus 3x squared. And so kind of writing that into the form that we have our f of x equal to 1 plus a 3x squared to the 1/3 power. And so in this case, what I want to do is a series expansion for r equal to 1/3, and I want to substitute into my expansion a 3x squared. So let's see what that might look like. So we've got a 1 plus a 3x squared to the 1/3. Now this will be my sum. So I've got a sum from n equals 0 up to infinity of my 1/3. Choose n, and I am substituting in 3x squared into my value for x. So what I have then is my sum, n equals 0 up to infinity, 1/3, choose n, and I have a 3 to the n and an x to the 2n. So if I write out the first 4 terms of that series, so if I've got my series 1 plus 3x squared to the 1/3 being my sum of 1/3 choose n, 3 to the n, x to the 2n, if I approximate the first 4 terms of that, when n is 0, I have a 1/3 choose 0, 3 to the 0, x to the 0, plus when n is 1, I have a 1/3 choose 1, 3 times x to the second. For when n is 2, 1/3 choose 2, 3 squared, x to the 4th. And then finally, as my 4th term, I have 1/3 choose 3, 3 to the 3rd, x to the 6th. So now I just need to calculate what are each of my binomial coefficients. So my 1/3 choose 0. Kind of like we do what we, in our usual definition, we'll always define our 1/3 choose 0 to be 1. So our r choose 0, that will just be by 1 by definition. For my 1/3 choose 1, well, now I have 1/3 minus 0 over 1 factorial. So that one becomes a 1/3. If I have a 1/3 choose 2, a 1/3 minus 0, a 1/3 minus 1 over a 2 factorial. And so that gives us a 1/3 times a minus 2/3 times a 1/2. And so in that case, we have a minus 1/9. So then finally, for our 1/3 choose 3, we have a 1/3 minus 0, a 1/3 minus 1, and a 1/3 minus 2, divided by 3 factorial. which that will in turn give us a 5 over 81. So now we can take these values and plug them back into our approximation. So this is going to give us a 1 plus a 1/3 times 3x squared plus a negative 1/9 times a 9x to the 4th plus a 5 over 81 times a 27x to the 6th. So if we simplify all of this a little bit, we have our 1 plus x squared minus our x to the 4th, and then plus a 5/3 x to the 6th. And so with that, we have our approximation for our series expansion out to the first 4 non-zero terms. So I hope you've enjoyed this kind of short description of what a binomial series is and how to work an example in one particular case. I will see you guys next time.